Look at any modern software release cycle, and you will see a mathematical collision. The development phase expands, consuming the schedule, while the testing window is violently compressed against an immovable launch deadline. Trying to exhaustively test every single line of code in this remaining sliver of time is a physical impossibility. Modern CI/CD systems operate on the assumption that a percentage of the codebase will remain unverified at launch. Releasing a system without 100% verification is a built-in reality of the architecture. But while incomplete coverage is an accepted reality, failing to test the exact components that hold the core system together is a massive failure of engineering leadership. When unidentified critical defects leak into the production environment, the organization pays an external failure cost. The resulting system downtime, immediate revenue hemorrhage, and regulatory penalties dwarf the cost of early detection. To survive this time constraint, engineering teams utilize a strategic framework called risk-based testing, or RBT. RBT is an analytical approach designed to isolate and eliminate the highest threat vulnerabilities. Its entire purpose is to maximize your defect detection percentage, the ratio of bugs found before launch versus after, strictly within that rapidly shrinking QA time box. This strategy allows teams to stop guessing. It replaces the broad panic of a looming deadline with a specific, evidence-based prioritization strategy that targets the most expensive risks first. This is a two-axis risk matrix. It is the foundational tool of RBT, used to replace subjective deadline anxiety with objective data. We map system vulnerability across two distinct variables. The y-axis tracks likelihood, the probability that a defect actually exists in the code. Technical test analysts calculate this by measuring architectural complexity, legacy code modifications, and the historic instability of third-party API integrations. The x-axis measures impact, the potential blast radius to the user or the business if that feature fails. Product managers and domain analysts plot this based on the frequency of core transaction flows and strict regulatory compliance requirements. When you plot these two variables against each other, the intersection creates a definitive heat map of system vulnerability. The dark red area in the top right represents critical risk, the exact modules carrying both high technical volatility and massive financial impact. Notice the opposite corner. This bottom left quadrant is low risk. These are highly stable features, like minor text updates or legacy UI, that have virtually zero impact on the core revenue-generating user journey. With the components canopirized, the matrix dictates exactly how much testing rigor is applied to each specific module. There is no more guessing. The matrix provides a mathematically sound blueprint for deploying limited engineering resources exactly where the threat is highest. Once the matrix is built, QA leadership has to physically allocate their engineers proportionally to those assigned risk scores. This is a standard QA time box. Under extreme pressure, sequentially testing from feature A to Z guarantees failure. Instead, teams execute a forced hybrid dynamic schedule to ensure critical paths are secured without leaving systemic blind spots. The first phase uses a depth-first approach, consuming roughly 70% of the available time box. Here, all efforts are focused vertically, drilling straight into the critical and high-risk quadrants we just identified. The most senior engineers are deployed here. They use intensive techniques like boundary value analysis, negative testing, and heavy automation to aggressively try to break the most essential business logic. This concentration of force is mandatory. You have to trigger these critical failures in the first few days at the sprint. Otherwise, the developers will not have the physical time required to rewrite the broken architecture before the release date. But precisely at the 70% mark, the strategy must abruptly pivot. The deep, targeted drilling stops, and the timeline transitions. The final 30% of the time box is dedicated to a breadth-first phase. The validation shifts horizontally, scanning across the medium and low-risk blocks to verify the connective tissue between the heavy modules we just secured. This phase relies on rapid exploratory testing and basic happy path user flows to confirm that the broader system integrates correctly end-to-end. By strictly enforcing the schedule, you guarantee that fatal business flaws are excavated and resolved early, while ensuring the broader system isn't pushed to production completely blind. New code often breaks old features. But when validating if existing logic is still intact, running a full automated regression suite is usually too slow for the remaining time box. To isolate the exact tests needed, engineers must aggressively curate their regression tests using an overlapping combinatorial sieve. We start with thousands of potential test cases. The first two filters are technical. Impact analysis uses dependency maps to find only the modules touched by recent code changes, while risk-based selection strips away any tests that aren't linked to our high-risk matrix quadrants. Next are the data-driven filters. History-based clustering targets bug clusters, the specific files that have failed in previous releases, while coverage-based optimization uses pairwise math to remove tests that check redundant logic paths. The final step aligns the tests with the business. Requirements traceability matrices catch side effects in connected logic, and operational profile logs ensure we prioritize the paths 80% of our users actually take in production. Stacking these 6 filters removes both technical bloat and human guesswork from test selection. What emerges at the bottom is an algorithmic extraction, the absolute minimum viable set of test cases required to validate overall system integrity under extreme time pressure. A highly tuned risk matrix and a dynamic testing schedule are useless if they only exist in a QA manager's private spreadsheet. For risk-based testing to actually work, it must be aggressively embedded directly into the engineering team's daily issue tracking workflows. These visual tags establish strict release-exit criteria that govern the entire deployment pipeline. The rule is absolute. If a development task carrying a critical risk tag has not been fully mitigated and tested, the CI/CD pipeline gate remains locked. The deployment is refused. Over time, teams must also guard against the déjà vu bias, the tendency to lazily assign the exact same risk tags every single sprint. This is corrected by feeding real-time production metrics back into the next planning phase, forcing the risk model to adapt to the reality of the software. Ultimately, RBT functions as a shared logic that forces the entire organization to agree on what constitutes good enough for release. It transforms deadline-driven panic into transparent, strategic quality leadership.